Okay, well, it's my pleasure to introduce Professor Lars Ruthotto from Emory University, who will speak on some of his recent research on a machine learning framework for high-dimensional mean field games and optimal control, where he solves very high-dimensional PDEs in tens and hundreds of dimensions. I'm looking forward to your talk. It sounds very interesting, and with that, I hand it over to you.
Okay, yeah, thanks, Justin, for the kind introduction, and thanks also for all the organizers for having me and for organizing this nice workshop. I'm looking forward really to the whole week and follow more of the other talks also. And in this very short 25-ish minute talk, I will show you a few recent works that we have done in this area. And then I hope for more discussions. So I want to look very briefly at two problems. One is optimal transport. So you map an initial density rho 0 to target density rho 1, as depicted here on the left, but not in 2 dimensions, but in higher dimensions, as Justin alluded to. Like think about 100 or so dimensions. And for this branch of work that we've been doing, I want to show you some application actually to machine learning, to generative modeling. And then I want to also talk a bit about using some of the numerical techniques that I'm going to show you to solve optimal control problems in higher dimensional spaces, and solving them in what we would call a semi-global fashion. So you solve an optimal control problem for many different initial states in our case. And those are recent works that my group and I have been working on over the last couple of years, also with collaborators at UCLA mostly, and Stan Osha's group. All came together in an IPAM program I was part of pre-COVID, and then we've been working ever since. So a lot of credits to my former student Derek Onken, and Stan's postdoc Semi, Levon, and Wuchen, and my current student Xingjian Li, who have been working in this. So I want to first talk about mean field games, mean field control problems, and how one can use machine learning techniques like neural networks to solve them in high dimensional spaces. So a mean field game is like an optimal, you can write it down as in a variation of form as an optimal control problem, where you have a state variable rho and a control variable v, think about velocity, that is governed by a constraint that is given by the continuity equation. So the continuity equation here models the density of all the agents and they are supported in RD, and D, think about it as being like 100 dimensions or so. So you want to find the control that minimizes some Lagrangian running costs. Typically think about transport costs as one example today in my talk, and then some other running costs that model, for example, congestion. So they're based on the density. And then some terminal cost that say, for example, how well do you reach the target allocation. Here's a 1D example. So you want to push samples from a normal distribution to this bimodal distribution while minimizing the transport costs, avoiding collisions, and avoiding some parts of the domain. So these mean field games are very powerful when you model a non-cooperative differential game with a large number of rational agents. So instead of modeling each agent, you basically model them or model their density with a rho. So that's a state. And those mean field games have really simplified a lot of things and enabled a lot of research in economics and other fields. There is another way to look at, so solving those in high dimension, just to make the point clearly, is going to be quite involved because, for example, you need to solve a continuity equation in high dimensions and then compute all the other quantities. What's useful to come to an effective solution is to look at the microscopic perspective. Basically, what you treat the problem as, you look at it from an agent's perspective, like a point in your domain in RD, and then that agent will have to make a decision. So there will be a cost just associated to that agent. Of course, still coupled with a rho here to the population density, but it's similar, has a running cost L and F and a terminal cost G. And here the evolution, also the update of the agent, is only dependent on the velocity. And you can see quite clearly, if you have taken a numerical PDE class, that this so this curve here that you compute is actually a characteristic curve for the continuity equation. Okay, so it's related to the method of characteristics. There are some recipes for how to design these functions f and g that I've highlighted here, so that they relate to the previous slide and that they make this microscopic viewpoint equivalent to solving the variational problem. Another important thing that we will actually use, so after looking at this problem from a variation perspective and from a microscopic perspective, I want to define the value function. So the value of an agent state, so if you start at x at time t, that is basically the minimal cost to go. So the minimal cost along this trajectory. And here again, like these blue curves are your characteristic curves of the continuity equation and are your optimal controls through the state space. So those problems are equivalent, and we can now get to PDEs, which this workshop is about, by looking at what properties does the value function have. And one important property is given by Hamilton Jacobi Bellman equations. So that's a backward in time PDE that depends on the Hamiltonian of the problem, which in turn depends on the Lagrangian cost mostly. So it's a terminal type condition. So at the terminal time, you know the optimal cost to go is basically given by the terminal cost. But then backward in time, you can solve this PDE, which I should highlight depends on the row. So the row is here. So why would you do this? In optimal control theory, you can derive that the optimal velocity is actually given by the negative gradient of this Hamiltonian at the gradient of phi, which you can use to plug this into the continuity equation, which was again the PD constraint that also simulates the population evolution. And then you get a PDE system consisting of the Hamilton Jacobi Bellman equation, which goes backward in time, and the continuity equation, which goes forward in time. Both are really tightly coupled, which sort of makes this an interesting area to work in. It's not so easy to break this forward-backward structure apart, and also thinking about high-dimensional PDE solver, which is what we are interested in here, because we cannot simply mesh the PDE as we saw so in other talks here. So the first contributions we have made here, and I'll only glance over it quickly because then I want to talk about some applications, is that we can eliminate the continuity equation with a Lagrangian PDE solver, which is mesh-free, and then solve the variational problem, where we plug in, basically we eliminate the V and use the feedback form from the previous slide to express it in terms of the value function, and then approximate the value function itself with a neural network. So that is kind of one way to break the curse of dimensionality, to kind of use a function approximator together with a mesh-free PDE solver here in the case of Lagrangian schemes. A few things we had to sort out. So when you do this, and you'll see this on a later slide, you need, from your neural network approximation, you need some gradients, some Laplacians. So we've developed some efficient algorithms for computing those quickly. We had some synthetic examples in that paper from OT and crowd motion up to 100D. Surprisingly, for two-dimensional case, we found that in our problem, the solution was actually competitive to a convex programming-based PD constraint optimization code, which is good because, as I think is known in this crowd, the neural network training problem is non-convex. In our case, it's at least smooth, but it's not so easy to guarantee really convergence. So we were surprised by that in 2 dimensions. And what we found important was actually to really look at the HJB and have a penalty function on that along the characteristics. So we're blending some of these ideas. I should say that there are many related works in this area. So by the time we worked on this, there was already one quite influential and nice paper about solving HJBs and with stochastic dynamics. Today, I'm only going to talk about deterministic dynamics and mean field games. So this paper did control with stochastic dynamics. What I'm going to talk about more is this application to continuous normalizing flows, which is a generative model in machine learning, where naturally these high dimensional OT problems arise. And then just mentioning that there are also extensions of this work. Okay, so that's basically setting the stage for the first part of today's talk, where I want to show how you can use these OT techniques for generative modeling. So a common way to solve generative models is to use what's called continuous normalizing flows, which is basically thinking about the change of variables. So the problem in generative model is depicted here on the right. You have blue samples from some unknown distribution, but you have also in the same dimension, you have a Gaussian distribution, which you can use to estimate densities. It's of course very easy, and you can also draw samples. So what you want to do is you want to find a mapping from this normal distribution to the to your samples. I can show you one solution here, and you can treat this as a dynamic program, or dynamic problem where you have an artificial time. So you can have these characteristics or these trajectories where each of these red samples gets associated with one of the blue samples. And the way to solve this is by doing what's called likelihood maximization. So you maximize sort of the implied likelihood of your samples. And so this is kind of the push forward of the raw one, if you wish. The problem with this approach, this is a very popular approach in machine learning these days. It works relatively okay. The issue here is that there is no uniqueness, of course. So basically any path that connects the blue dots to the red dots works exactly in the same way. So if they start and end in the same point, it doesn't matter what happens along the way. And I depicted here one path that is not so nice. So if we want to use this mean field game framework and optimal transport theory, then we can change this this formulation by measuring transport costs and penalizing them. So that's actually maybe not such an original idea. There were already like a few works also to realize this. But then what was our contribution here was the numerical treatment of the problem. So just to show you how this would work. So these first two terms are the same one from the previous slide, but then I've been adding a transport cost. So the CL here measures the norm of the gradient along the trajectory. So this penalizes the velocity or the norm of the velocity, similar to what you have in Wasserstein 2 optimal transport. And then also a penalty here where I'm basically penalizing the HJB in a strong form also. And those ones, I should say, are computed along the trajectory, individual for every sample point. So if you do this on my problem here, so without these additional terms here that we've added, you can get trajectories like this. When you enter them, optimal transport theory guarantees you that you can have straight trajectories here between almost any densities. And that is nice because the uniqueness makes the problem more well posed, but also it allows you to use much more efficient time integration. So if you think about solving this problem here, which is in the end like training problem similar to neural ODEs, your ODE solver will benefit from having straight lines here. And those benefits of OT have been observed very widely. As I said, also before we started working on it, there were a few papers realizing this. But then again, like the numerical treatment of the phi and also the penalties were sort of what made our approach actually quite efficient compared to those. Just in very short, at the backbone of what my group has been doing, there is a specific model for the neural network. Namely, we model the network as a space-time dependent function, which you need in terms of the theory. You know that the phi is space-time dependent. Typically, we have a neural network part, and then sometimes we have a quadratic polynomial also, just to have more flexibility and more linearity also in the model. We like using ResNets for the forward propagation, and I sometimes like to write this out because I want to emphasize that in the end, what you need is the gradient of the network as well. So you can get that by backpropagation, but you also need the Laplacian. And here with the Laplacian, it becomes a bit tricky, because if you challenge yourself and you want to compute the Laplacian of a neural network with automatic differentiation, which of course is ubiquitous and also easy to use, you're really limited to matrix vector products. So if you think about the dimension being high, you would need D matrix vector products to compute the Laplacian. That can become costly, because you always need to traverse your computational graph. You can use trace estimators, but that makes the training more inaccurate, or the gradients more inaccurate. And what we found is better to derive the Laplacian manually and then have an efficient algorithm for that. And just to show you how well that works, my student Derek has done a comparison. So here are different dimensions of the problem, so 43 up to 784. And what he looked at is if you use the trace estimator, which is sort of the state of the art in machine learning for this computation, with a growing number of vectors. So you start with 1 and then you go up until the number of dimensions. And you time it on a GPU, I should say, so the parallel environment. Basically, our exact trace computation, which is this dashed line, is as efficient as one matrix vector product, which means that we can reduce it, we can make the gradients of the objective function much more accurate without adding any computational cost in terms of time to solution. So that was really great, especially because these trace estimators converge really, really slowly. And they are made for large dimensional problems, and these are actually pretty tiny matrices. I mean, you wouldn't use a trace estimator for a 700 by 700 matrix, I suppose. The difficulty is that you can only access it through matrix vector products. So anyway, we have worked these things out, so that's great. And it has led us actually to quite substantial reductions in the training time. So these are data sets from the UCI database. What you can see is two things. So we are always this triangle, and you want to be closer to the origin because that's fewer parameters and better quality in some measure. And you want to be closer here to the origin because that's smaller testing time, smaller training time. And I should say, especially in the testing time, so when you want to use variational inference and we want to get likelihood estimates, that's where these Laplacian computations really become key. Because if you cannot compute those efficiently, then you will have to have this for loop over D terms of automatic differentiation. So that was very nice. Again, work from my student Derek. I have reference to his paper later. He presented this at AAAI this year. And the paper also has more examples on other distributions. So more recently, we have then said, let's look at other type of control problems. And specifically, we were inspired by multi-agent problems, where you have not enough agent to go to the mean field limit, but also like more than one agent, okay? So here's one example I like to motivate this work with, because we can plot it very easily. And this is a game between two players. So you have a blue and an orange player, and they need to go through this corridor and they need to reach their targets. And so they must avoid this wall, and they must avoid bumping into one another, which is why we have the safety bubble. So you can think about this as a COVID example where everyone needs to leave a room and not bump into one another. So in this case, we wrote down the problem in a hopefully similar way. So we have some running costs that depend on how much you're moving. Then F and Q are interaction costs between the different agents. So for example, Q will be collision avoidance, like a penalty for getting too close to one another, and the other one will be that would be obstacle, and the other one would be for collision avoidance and some terminal cost as well. And we have now we have an ODE system, so we work similarly. The work is now similar to the microscopic viewpoint, where you have the X giving the state of all the agents of all the system. You can think about if you have n agents, then this system can become quite large quite quickly. But what we're really aiming to achieve here is to extend our work from mean field games to problems where you only have an intermediate number of agents. So think 50 or 100 or something like that. For that, you would not model the whole population as a density. So actually, we've realized that a few things simplify, and then a few things also, of course, become more complicated, especially when you have nonlinear dynamics F here. But in very short, since I'm a bit pressed for time, I want to kind of see or show you a few modeling, how to model this problem and how then it performs and why this could be interesting. And I think Karl Kunisch probably will also add to this because he's worked in this area and he's going to speak later this week. And I'm looking forward to his talk on this one. So the idea again is to learn the value function of the optimal control problem, because from that, under some assumptions on the Hamiltonian, you can obtain the control through a feedback form. And ideally, I would want to get the value function everywhere in the state space, but I'm going to be a bit more modest and say I want to get this value function semi-globally. And by that, I mean, it's really crucial to understand what I mean is I want to get it in parts of the parameter space that are likely to get visited in some sense. And how I model this as follows. So I will draw an initial state of the system from a distribution rho 0. So the x will be sampled. Then the dynamics itself is deterministic. And I'm minimizing sort of the control objective for the path that I have. And by choosing this distribution of initial states, you sort of can fill up some of the state space that gets sampled in the training process, and along which we want to solve the HJB, but also keep an eye on the objective function here. And then, similar to what we've seen before, so we'll model actually the dynamic Z through the feedback form. So we'll use the Hamiltonian for that. Then we will accumulate the running costs along these trajectories, as we've also done for the generative modeling problem. And also have a penalty here for the HJB violations, which was kind of important for us. And appears actually also in the literature in related approaches. We'll use the same neural network parameterization than we had before. Note here again that there is a gradient of phi coming in. In this case, since we have a deterministic dynamics, we don't need to compute the Laplacian, but we are currently also working on stochastic extensions where that may be good. There is another interpretation of what's going on here. So not by the method of characteristics that I think was quite natural for the mean field games because you have a continuity equation there. But you can link this now to the maximum principle, because that is dictating the optimal trajectories here. But you note that that the dual variable in the PMP is basically the gradient of the value function here. So again, the value function will be what we parameterize within the neural network and then train the weights. When we train the weights without knowing any solutions of the control problem, so by directly minimizing the original loss function, but also the HJB penalty, which are necessary conditions. So here's one thing that is sort of an interesting test case for our example from before. So these clouds here illustrate where we draw the initial states from in the training. And then we've done some things after the training. What we've tested out is, so how now would the system react if we perturb the state of the system at some point that was not anticipated in the training. So here after 0.1 time 0.1, we take the system, we apply some random shift to it. And what you can see is that basically then in a classical optimal control setting, what you would have to do is you would realize you're in a new state and you didn't plan for that. So you would have to solve the nonlinear program again for getting in or to get a new control. Here, what we've done is we've just blindly followed the optimal policy given by the neural network and kind of see what happens here. And you can see, for example, in the case on the right, which is a much larger disturbance, and we picked it precisely so large so that the orange player here really leaves the training region. So it's very unlikely that this was a case visited in the training, but in some way, the network actually for this case behaved quite well, which we currently have no theory for. Would love to have more theory here, but at least it was a good sanity check, because you read a lot about instabilities of neural networks and small perturbations having a dramatic effect. Here we have one example where at least things look much better. We of course also compared suboptimalities for the control problem and so on. There are more details in the paper, and it works relatively competitively and is okay to train. So here, notably, this network only has like 1,000 weights or so. We have more like higher dimensional examples also in this paper. We have like a 150 dimensional problem where the dimension increases with the number of agents. This is 50 agents. So again, not enough for mean field limit, but also enough to get this problem or make this problem challenging. Then of course, training time becomes more costly, go from 10 minutes to about an hour, but not really what you would expect from exponential growth of the computational cost and the curse of dimensionality. So with that, let me just sum up quickly and see if we can take some questions here. If you have questions later, you can also email me at this email, or I'll find you in one of the sessions and maybe in the interactive sessions here. Great.
Thank you, Lars, for the very interesting presentation. Are there any questions? Wei, please go ahead.
Okay, thank you for the nice talk. I think at the beginning you mentioned that you're solving this problem using so-called semi-global.
Yes.
Can you elaborate a little bit? What is the meaning of a semi-global here,
yeah.
and how did you approach that goal?
Yes, let me show you a picture here. So by semi-global, so ideally, I would solve the HJB everywhere. Like in this whole, it's a 4-dimensional state space because we have 2 players, 2 state variables for each, right? But I don't think, I would be hesitant to say that we can do this without running into the curse of dimensionality, because I would have to sample everywhere to make sure that I'm solving my PDE. So again, I want to be on the cautious side and say I'll solve it semi-globally, in the sense that we draw the initial states here in those 2-point clouds. From each of those samples, our agents will find some way. So this one is more closer to the training, because in the training we don't have this perturbance. So you have trajectories that look like so. And this means that points probably in this region will be sampled quite frequently. And since we penalize the HJB, we only observe the PDE along this trajectory. I'd have higher hopes the PDE is solved well here than, say, in this bottom left corner, because that's a case where we never sampled from. And it's a similar thing, I think, maybe in your work you have made similar experiences, because I know you've also worked in this area, because your loss function depends on the current control. So on your estimate of the value function, and that is really a part that makes these type of problems very difficult.
Okay, yeah, thank you.
Sure. It was a great question, actually. So,
are there any other questions?
doesn't look like that. But again, if anyone has questions later, I'm quite easy to find these days.
Well, thank you for the very nice presentation.
Yeah, thanks again for having me.